The new pictures obtained from the James Webb Space Telescope have dumbfounded researchers, uncovering a startling reality about the universe rather than simply broadening our perspective on the cosmos. These pictures have revealed a troubling truth: our current understanding is insufficient to grasp the possibilities of the universe in its earliest stages. The prevailing theories regarding the universe's origins appear to be reaching their limits, urging us to rethink new hypotheses about its beginnings. This raises a fundamental question: how was the universe shaped, and why? These discoveries challenge even the most experienced astronomers. Consequently, there is a need to explore the true nature of the Big Bang and its ever-evolving intricacies. It may be time to reevaluate the Big Bang theory itself, as common interpretations have often misrepresented it. The Big Bang wasn't merely an explosion within pre-existing space, but rather the actual beginning of space itself, unfolding around 13.8 billion years ago alongside matter and time. One of the critical concepts in science and cosmology is the idea of a singularity, a point where gravity becomes so intense that the curvature of space-time becomes infinite. Billions of years after the universe's creation, we now understand that our cosmic home exists as part of a vast collaboration. For scientists, this highlights a pivotal aspect of the universe's existence: its ongoing expansion. The universe doesn't simply drift into pre-existing space, rather, space itself continues to expand as supported by standard theories. The first stars are believed to have begun shining roughly 200 to 300 million years after the Big Bang, marking the end of the so-called dark age of the universe. This was the era when the first bright celestial objects assembled to form mature galaxies. However, the speed at which these galaxies developed remains a mystery. A significant breakthrough came in July 2022 with the James Webb Space Telescope's first images, which revealed various galaxies, some of which already existed around 300 million years after the universe's birth. Despite being much younger than the galaxies we observe today, these early systems were significantly smaller and less massive, aligning with the scientific model of the time. In the early universe, the density of matter was insufficient to create galaxies as large as those we see today. The discovery began with 6 remarkable redshifted bright spots identified by the James Webb Telescope, triggering one of the most significant cosmic mysteries in recent times. These newly found galaxies, although similar in age to previously recorded ones, appeared almost as large as our Milky Way. This finding has sparked intense interest in Big Bang cosmology. After analyzing a series of images taken with the telescope's near-infrared camera, scientists confirmed the presence of these distant objects using redshift data. They determined that the light from these galaxies had traveled for over a billion years before reaching Earth. Thus, these galaxies existed between 570 and 700 million years after the confirmed Big Bang event. This remarkable discovery challenges conventional cosmological assumptions which predicted the formation of much smaller, less developed galaxies at this stage of the universe's history. Instead, the James Webb Telescope revealed galaxies nearly as large as the Milky Way, defying expectations. The gravitationally bound stars in these galaxies had already amassed more than 10 billion times the mass of the Sun. One of these galaxies even showed signs of a mass exceeding 10 billion solar masses. However, the accuracy of this theory remains uncertain. Even if true, the mass present in the early universe would be far greater than previously predicted, deepening the mystery. The discovered galaxies challenge almost all conventional cosmological theories. If even one of these galaxies is confirmed It would force us to reconsider our assumptions about the formation of early cosmic structures. The density of matter in the early universe would need to be far higher than previously thought. Another possible explanation is that these galaxies formed in an entirely unknown way. These revelations demand a re-evaluation of the Big Bang theory. Many astronomers are baffled by these findings, often voicing their concerns in scientific publications. Those who question current theories are frequently labeled as radical or extreme, yet even proponents of the Big Bang theory are faced with unresolved questions. These questions include fundamental concerns. How could something emerge from nothing? 13.8 billion years ago, was there a trigger for this event, or was it purely random? Stephen Hawking famously argued that the concept of time as we currently understand it began with a Big Bang. Thus, this process could not have been initiated by something external or caused by an external trigger. Similar questions arise about the uniform distribution of radiation and matter across the universe. No matter where we look, we observe a similar arrangement of galaxies, nebulae, and radiation. Modern scientists explain this phenomenon through the theory of cosmic inflation. However, others have expanded this idea, proposing that the universe has expanded in a turbulent way. According to this theory, expansion occurred only in isolated regions like bubbles, while other areas continue to expand indefinitely. This model raises the intriguing possibility that other universes could exist within these expanding bubbles, each governed by its own set of physical laws. This perspective suggests that our universe might not represent the entirety of existence, but rather be just one part of a much larger and more complex structure. Within this framework, the idea of an eternal cycle of collapse and rebirth for the universe has been proposed. However, this view is far from the dominant perspective in cosmology. For example, in 1955, an article published in NASA's Hot Shot magazine suggested that the universe may never have experienced a Big Bang and that it has always existed, possibly for an infinite period. In this interpretation, the expansion of the universe would simply represent a phase in its infinite history rather than a singular event. This steady state model, though largely abandoned by mainstream cosmology, highlights the enduring mysteries surrounding the universe's origins and evolution. Even today, cosmologists debate whether the universe has a definitive beginning or if it represents an eternal cycle of expansion and contraction. The idea of a multiverse where countless universes exist alongside our own further complicates these discussions. If true, it would mean that the Big Bang was merely one of many such events, each giving birth to its own universe governed by unique physical laws. The discoveries made by the James Webb Space Telescope have reignited these debates, challenging previously held beliefs and forcing scientists to confront new data that doesn't align with established models. Whether these anomalies signal the need for entirely new theories or are simply deviations that will eventually fit into the broader cosmological framework remains to be seen. In the meantime, these findings underscore the importance of continued exploration and openness to alternative ideas. The universe is far more complex than we ever imagined, and every new discovery brings us closer to understanding the intricate tapestry of its history and structure. While definitive answers may still elude us, the pursuit of knowledge continues to push the boundaries of human understanding, reminding us of the vast, mysterious cosmos we call home, non-existent with the continuous development of the issue, giving the impression of steady improvement after some time. One of the additional charming speculations rises out of the domain of quantum physics and string theory. A few tests have proposed that our universe, and everything inside it very well may, be a projection or reproduction from a higher layered reality. While this might seem like a plot from a sci-fi film, it has associations with a Kardashev scale, which estimates a progress degree of energy use in light of its capacity to harness the force of a whole world. Assuming a Type 3 civilization existed, capable of using all the energy of a universe, it could have made an ideal reenactment of a universe. However, affirming the validity of such a situation presents a huge test. Investigating the depths of cosmology and the beginnings of the universe leads us into an area of great mystery and continuous scientific inquiry. The new pictures caught by the James Webb Space Telescope have reignited debates about the actual texture of existence, testing laid out hypotheses and empowering scientists to re-evaluate basic parts of how we interpret the universe. Key to this discussion is the theory of the universe's origin, which serves as the underpinning of current cosmology. As per this theory, around 13.8 billion years ago, the universe rose from a dense and hot state, expanding rapidly and leading to the space-time and matter we observe today. This titanic event wasn't a blast in prior space, it also marked the beginning of space itself, the concept of a singularity where gravitational forces are so intense that the curvature of space-time becomes infinite. Aids support how we interpret this beginning phase of the universe. However, the discovery of mature gigantic galaxies within a couple 100 million years of the Big Bang challenges traditional thoughts about the speed at which the first structures formed. These discoveries suggest that the early universe had a much greater density of matter than previously estimated. This raises the question of how such massive structures might have developed so rapidly, forcing cosmologists to rethink how galaxies such as those observed by the James Webb Telescope formed so early in the universe's history. One key question arising from these revelations is the theory of cosmic inflation, which suggests that the universe expanded dramatically in the first moments after the Big Bang. This rapid expansion is believed to explain the uniformity of the cosmic microwave background radiation that we see across the universe today. However, recent discoveries are complicating how we understand the early universe's development, suggesting that we may need to revise our inflationary models. The formation of these early massive galaxies raises fundamental questions about the role of dark matter and dark energy, two mysterious components that make up most of the universe's mass and energy. While dark matter is believed to provide the gravitational framework necessary for galaxies to form, scientists still lack a clear understanding of its distribution and properties in the early universe. In light of these unresolved mysteries, theoretical physicists are considering alternative cosmological models that challenge the standard theory of the Big Bang. Some of these hypotheses suggest that our universe could simply be one of many in an immense multiverse, each governed by distinct physical laws and constants. Such ideas, emerging from string theory and quantum cosmology, present a more complex and interconnected universe than previously imagined. One hypothesis gaining traction is that of eternal inflation, where universes are continually formed within a larger, expanding space. This suggests that our universe could be one bubble among an infinite number of others, each with its own physical properties. The challenge, however, lies in finding observational evidence to support these speculative ideas as they push the limits of what can be tested experimentally. Another provocative hypothesis proposes that our universe might exist inside a computer-generated simulation, drawing parallels to advancements in artificial intelligence and computational science, where simulations can replicate complex systems. If true, this idea would fundamentally alter our view of reality and raise critical philosophical and scientific questions about the nature of existence itself. As observational astronomy continues to advance, instruments like the James Webb Space Telescope, with its unparalleled sensitivity and resolution, promise to uncover many more of the universe's mysteries. Future observations might provide further insights into the earliest moments of the universe, potentially offering clues about its ultimate fate and the fundamental principles governing its ongoing development. In the meantime, particle physicists remain focused on understanding the fundamental particles and forces that shape the universe. The quest to unify gravity with the other three fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, remains a central goal of theoretical physics. In the realm of quantum mechanics, debates about the nature of time persist, with some theories suggesting that time itself may be evolving, or perhaps more subtly at the most fundamental levels. Understanding the nature of time within the context of cosmology could revolutionize how we interpret the universe's origins and development. Moreover, the search for extraterrestrial life continues to inspire both public interest and scientific inquiry. Discovering exoplanets, planets orbiting stars beyond our solar system, has expanded our understanding of planetary diversity and the potential for habitable conditions elsewhere in the universe. Future missions such as the James Webb Space Telescope's investigation of exoplanet climates could uncover bio-signatures that point to life beyond Earth. As scientific exploration pushes forward, so to do philosophical inquiries about humanity's place in the universe. The search for answers to questions about existence, the possibility of intelligent life elsewhere, and humanity's future in space exploration will continue to drive discussions across scientific and philosophical disciplines as humanity pushes forward in its quest for knowledge. The boundaries between science, philosophy, and technology become increasingly blurred. The advancement of artificial intelligence, for example, raises profound ethical questions about the role of machines in our society and their potential to surpass human intelligence. The development of advanced AI systems capable of making decisions and solving complex problems could reshape the future of scientific discovery, potentially aiding in areas like astrophysics, cosmology, and particle physics. However, this also introduces concerns about the control and accountability of AI, especially when it comes to matters of life ethics and governance on a broader scale. The continued exploration of space could offer new frontiers for humanity as we venture beyond Earth, establishing colonies on the Moon, Mars, and beyond. We will need to rethink what it means to be human in the context of a vast and expanding universe. Space exploration has the potential not only to uncover the mysteries of the cosmos, but also to challenge our understanding of life itself. What if life exists elsewhere in the universe, thriving in environments we never imagined? What if intelligent civilizations are already out there, waiting to be discovered? These questions stir our collective imagination, pushing us to explore the unknown while confronting our place within the universe. The quest for knowledge also invites us to consider our philosophical views on existence. Are we alone in the cosmos, or is life a common phenomenon across the universe? How do our beliefs about the origins of life, the nature of consciousness, and the future of humanity shape our actions and decisions? As technology advances and we continue to make new discoveries, we will be forced to confront these questions head-on. Ultimately, the pursuit of scientific knowledge and the exploration of space are not just about uncovering facts and figures. They are about understanding who we are, where we come from, and where we are headed. As we unravel the mysteries of the universe, we must also reflect on our responsibility to protect our planet, preserve the wonders of life, and ensure that the advancements we make benefit all of humanity. The future, as we continue to push the limits of knowledge and discovery, holds infinite possibilities, and it is up to us to shape the path forward, guided by curiosity, ethical responsibility, and a shared vision of progress.